Hello, this is Frédéric Goriot from Paris South University, Laboratoire de Recherche en Informatique. Today, I'm going to talk to you about spatial types, which is a new scheme you use to specify complex cellular automata, which you need if you explore artificial physics. Automata is a classic model of computation. It uses a lattice, such as a 2D grid of finite state automata. Each automata exchanges state between neighbors and uses a lookup table to find next state. CA are usually simple. For example, the game of life rule uses 1 bit of state, represented as a dot here, and 29 gates. Each cell makes a sum of its 8 neighbors, and depending on this number, it will be born, die, or survive. And if you start with this initial configuration and update synchronously all the cells with this rule, you obtain an oscillating behavior. People usually do such simple rules because already with such simple rules you can have universal computation, and also because the inherent formalism of lookup table is limited to 1 or 2 bits of state, simple state, and immediate neighborhood. I'm interested in complex CA, and I propose in this talk a new scheme to implement and simulate the complex CA, because I want to do general purpose computation on CA. And this is inherently complex. I will now present you a rule which uses 77 bits of state and near 14,000 gates. I use a hexagonal grid. Each color in this little square indicates the state of the cell. There are membranes which are being simulated, connected by channels, red channels for vertical connection, green channels for horizontal connection. Instructions are sent from the host as waves which sweeps through the medium, the blue waves, and they trigger division of channels and membranes alternatively. Division of membranes is done using a strangle force. Also, there is also force, repulsive force between adjacent membrane, which causes homogenization through the medium. So the resulting execution, the specific set of instructions trigger the alternative division between channels and membranes, which generate the 2D grid of membranes connected by channels. Columns, you can see columns here, and lines here. So what is the domain of application for complex CA? In general, the method that I propose is adapted for artificial physics. The general purpose cellular automata that I've just shown you uses biologically inspired physical artifacts such as membrane, forces, waves, channels. The physical law are rotation invariant, and spatial types fit physical law because they embed rotation invariance, because they use reduction heavily or only. Reduction means applying associative commutative operators such as the sum or the minimum or the maximum. And because it's commutative associative, the particular order that you use doesn't matter. For example, the game of life uses a sum reduction on 8 neighbors, so if you rotate 90 degrees, it will still work the same way. Compared to the game of life, as you will see, spatial type uses 12 different neighborhoods to do any kind of reduction, so it has a much improved expressiveness. The meat of my talk is presenting spatial type. Data consists in field over set of 2D points. The sets are called locus. Operators of spatial type consist mainly in reductions that are applied to one field and produce another field. We'll consider blobs, which are connected set of points, and illustrate simple computation of blob features such as the frontier of a blob. We will then compose several reductions to compute a non-trivial field called meet, or meeting points, which is useful to preserve connectedness of blobs when moving them. Finally, we'll show how to define a sequential circuit that can be iterated, and we'll build a specific circuits that compute a discrete Voronoi diagram. This circuit will use a meeting point that we'll define in point 2. So let me now introduce spatial types. We call locus a set of 2D points, and we consider 3 locus associated to a planar graph: the vertex, the edge, and the face in light grays. We will focus on triangulated planar graph. So here an edge is missing. Our approach works for arbitrary triangulated planar graphs. However, we'll consider regular hexagonal lattice for simplicity. We'll forget about the graph and consider only the locus, the 3 sets of points, vertice, edge, and face. And we do a tiling of the space using a kind of Voronoi tessellation. Vertice gets hexagonal tile, edge gets square tile, and face triangular tile. And we forget the points. We consider Boolean fields, which are a function from locus to Booleans. Here, it's a vertex Boolean field, which has 3 true values for these 3 vertex, and we represent such a Boolean field by painting the associated tiles. This is a vertex Boolean field called bool v. We also consider edge Boolean field, which is a kind of a frontier here, and face Boolean field, which is the inside face of these little blobs. The Boolean fields have an arity, which is 1 for vertice, 3 for edge, because there is 3 times more edge, 2 for face, because there is 3 times more face. We also consider integer field with only 2 or 3 bits, and the bit density of the integer field will be defined as the number of bits, 2 or 3, multiplied by the arity. Consider a bool Vx encoding 2 blobs which are connected components of vertex. We want to compute the frontier of these 2 blobs, which is a set of edge, therefore a Boolean edge field, bool E. We need to compute the XOR of the 2 bits adjacent to each edge. We'll go from vertex to edge by passing through 2 intermediate locus called transfer locus, noted EV, small e, big V, and small v, big E, VE. Each of these 2 intermediate locus gets its tile here. So we start from on the vertex with 2 bits that we want to make the XOR of. Then we broadcast them to a bool EV by duplicating 6 times the bits. Then we transfer them to a bool VE, which is associated to the edge by just making a communication. And finally, we make a reduction of 2 bits into 1 bool E. This computation can be compiled into a circuit. A broadcast will generate a fan-out wiring, a transfer wire segment crossing the tiles, and each XOR reduction is compiled into a single XOR gate for each edge, but there is 3 edges for each vertex. Therefore, the gate density of frontier is 3. We can do a similar computation for vertex. It would need 5 gates, and for face, it would need 4 gates because there is 2 face and 2 gates. So this new transfer locus divides the locus tile into subtile, a bit like this stained glass. We have the EV and VE that we've just seen that allow communication between vertex and edge. We also have VF and FV transfer to communicate between vertex and face, and also FE and EF to communicate between face and edge. So the whole situation is symmetric, and we have broadcast and transfer, which are also symmetric. Each of these 6 locus can define 2 reductions. One towards the center, from 6 to 1 here, but also another reduction towards the other locus. So those 2 can be applied XOR to generate this one, those 2 XOR to generate this one, and so on. The same applies to the 6 transfer locus. Okay, there are 6 of them. So 2 reduction for each of the 6 locus. It makes 12 possible neighborhood for doing a reduction. What we have done with XOR, we can also do with OR, with AND, or with plus, as long as it's associative commutative. To avoid repeating broadcast transfer reduction, we define composite operation. For OR, we call it exist. For AND, we call it for all. For delta, for XOR, we call it delta. For sum, we call it sigma. Using a single such composite operation is sufficient to compute interesting feature of blobs. We've seen that the frontier can be computed with a delta, the XOR. With for all, we can compute the inside, the edge inside the blob. Those 2 operations have radius 1 because it's an edge field computed from a vertex field, so they are neighbors. We will now see 3 operations with radius 2 because they imply a communication from vertex to vertex. And the distance now is 2, so the radius is 2. By combining 2 exist combined operation, we can compute the neighborhood of the blob. And last, we have 2 vertex frontiers, the one which is inside by ending with X, and the one which is outside by ending with not X. So when the planar graph is triangulated, the 2 transfer locus of each face are facing each other. So we can define a central symmetry to exchange them. So the summit is going to send to the base. Okay. The central symmetry in terms allows to define a communication between each vertex with its apex edge, not the edge immediately adjacent, but the one here. By first doing a broadcast, then a transfer to the face, then a central symmetry, then another transfer, and then a reduction on the edge. So this will work only for maximal planar graph. So we are now going to see how to compute a non-trivial field called meet of X, or meeting of X. Consider a bool V representing 2 blobs here. The merged vertex are the vertex which are adjacent to 2 distinct blobs, and the merged edge are the edge adjacent to the out frontier of two distinct blobs. The same concept exists, but with respect to holes. The div vertex are the vertex adjacent to two distinct holes, and the div edge adjacent to the out frontier of two distinct holes. What we want to compute is the union of division and merge points, which include therefore vertex and edge. Why are we interested in this? Because if we don't modify a vertex, the mid vertex, we want merge blob, we want divide blobs. And if we don't modify flip simultaneously the two vertices adjacent to a mid edge, we want also merge two blobs or divide two blobs. So preserving each blob is possible if you know the meeting vertex and the mid edge. Let us see now how to compute the meeting points. First, let's look at the vertex meeting points. We need to compute the number of local connected components of blobs in the ring of the 6 neighbors. Here it's 2, and here it's also 2. If this number is greater than 1, then it means it's a meeting vertex. Either a dividing vertex, if it was full and we empty it, it will divide, it will cut the blobs in two, or a merging vertex, if it was not on and we put it on, it will merge the two locally. Each piece of local connected component must have 2 edge frontiers in the blob. One here, one here, one here, one here. And those edge frontiers are apex neighbor of the vertex we are interested in. Where are apex neighbor, where apex is the communication we've just seen. So to compute the number of local connected components, we consider the frontier, we apply the apex communication, and when we sum this, and finally we divide by 2. This costs 20 gates, and otherwise just 4. In order to compute the meeting edge, we have to consider the rhombus around the meeting edge and check 2 conditions. First, that there is no edge frontier within it, and second, that the 2 immediate neighbors are in the vertex frontier. The absence of edge frontier in the whole rhombus is computed using 2 for-all operation, and the presence of 2 vertex frontier in the immediate neighborhoods needs 1 for-all operator. The whole computation takes 18 gates and has a radius 3. Let us now look how to build the sequential circuits which can be iterated. A configuration is just a set of stored fields called layers. And a sequential circuit is just a function specified using spatial operation, updating a configuration. The complexity of a circuit is measured by the radius, the total number of gates, and the number of memory bits. Our first example of circuit is a very simple circuit, which uses a bool V vertex layer, 1 bit, and replace it by the neighborhood. So we have blobs which grows until they fill the whole space. We consider a one-dimensional version of this because for this simple circuit we're able to picture the whole circuit which is compiled from the formula of neighborhood, which I recall is the composition of 2 exist operators. For each of these exist, 1 OR gate is generated. The bit of is stored in a square cell here, is fed into neighbors and then back into it at each time step. It's a sequential circuit. How about now we consider a composition of 2 neighborhoods. It will grow 2 times faster using double number of gates. And this shows that when you increase the expression size, you increase the radius, but the circuit's complexity augments only linearly with the radius. So naturally, when you use special types, you have expression with high radius, but this is no problem. This is handled effortlessly. We will now show a non-trivial example of circuit computing the Voronoi diagram. At t equals 0, we start with 4 gray seeds, light gray, and we let the seed grows using the preceding growing, computing the neighborhood, except we don't grow next to meeting edge or on meeting vertex. So we are going to reuse the circuits, the logic gates, 38 logic gates computing the meeting point, but we had 14 gates to compute those little things. So we end up with a circuit of 52 gates and reduce 4. The Voronoi diagram appears progressively as the meeting point of the gray Voronoi cells. Conversions happen at the time which is equal to the half of the diameter of the grid. And at the end, the gray is marking the strict Voronoi cell. By strict, it doesn't contain the points which are adjacent to another Voronoi cell. The VDE contains 3 vertex, which is this vertex, which is equidistant to 3 Voronoi cells. And it is detected because it is in the outside of the Voronoi cell. It's not adjacent. This also works for point adjacent to more than 3 Voronoi cells. Designing CA with spatial type is very different than designing CA in a classic way. In a classic way, you use a regular lattice of finite state automata, which exchange state between neighbors using and compute the next state using a lookup table. When you use spatial types, you first of all, you don't need to have a regular lattice. You can use any triangulated planar graph. Although if you use a regular lattice, you are going to generate a cellular automata in classic ways. You don't use finite state automata, but only bits and gates. And you map them on vertices, and not only on vertices, but also on edge and faces of a planar graph. And not only on vertex, edge, and face, but also in between those on the transfer locus, which there are 6 of them. And you compute fields from other fields using reduction and also communication. Spatial type will allow you to build complex CA. First of all, it allows you to handle high radius. Then it exploits symmetries to factorize computation. For example, the edge frontier I've shown you. If you use a classic CA, you'll have to store it on the 2 adjacent vertices, whereas it's naturally stored on the edge for a single time. It does not require a crystal regularity, so you can think, one can think about simulating it on an amorphous medium, which is regular but not crystal regular. It can be compiled into a circuit and simulated efficiently. On a CPU with SIMD capability, you can compute 64 gates in a single instruction, working on 64 bits integer. And last, programming is modular. In this talk, I presented you computation such as the edge frontier or the neighborhood or the meeting point, and these computations were reused all the time. And this is maybe the most important property.